Good evening, everyone. I'm Rahul from IIT Madras. I'm PMRF PhD scholar and I'm NPTEL, PMRF NPTEL TA for this course EMI, EMC and Signal Integrity, which is taken by Professor Amitba Bhattacharya from IIT Kharagpur. So this is a third live problem solving session. So here we will be solving few problems based on the week 3, and the idea is that the problems we are solving, they are going to help you in that corresponding week's assignment problems. So let's start with brief introduction of, or let's say just a brief summary of what has been discussed in week 3. I hope I'm audible. If you have any doubt or any issues in seeing my screen or hearing my voice, please let me know. And I request you, if you have any doubt during the session, please unmute yourself and you can ask the problems. So let's start today's session. So last week, Professor has discussed about the spectral bounds of a trapezoidal clock, effect of duty cycle on spectral bound of a clock, and effect of rise and fall time on the spectral bound of a clock, and effect of ringing on spectral bound of a clock. And spectral bounds for linear system output was also being discussed. So in the first part, the spectral bounds for a trapezoidal clocks were discussed. So let's say we have a trapezoidal clock or a pulse train which has a trapezoidal signals. So it's a periodic pulse. So let's say this is our x of t, and this is the time axis. So now if we want the spectral contents, we need to convert it into the frequency domain. So in that, if that we will see if the that signal will look something like this. So this is expansion coefficient Cn. So for a, we have seen that for a spectral bounds of a trapezoidal signal looks something like this. So there are two breakpoint frequencies. This is f1, f2, and here it's 0 dB. So the DC, it's a DC value, and after that there is a drop of minus 20 dB per decade. And similarly, after f2, the breakpoint frequency, it becomes minus 40 dB per decade. So if we see that as we go above, so along this x-axis, the higher frequencies are reducing at, after f1, they are reducing at a rate of minus 20 dB per decade, that signal strength. And after f2, the second breakpoint, the higher frequency signals, their spectrum is or their magnitude is reducing at a rate of minus 40 dB per decade. So that's why, like, we study the spectral bounds and what kind of the trend they follow. So they look something like this. Actually, it looks something. It's a sync function, right? So now if we draw this correctly explains it. So it's kind of an envelope for that highest amplitude. So it actually looks something like this. And then we study the effect of duty cycle on a spectral bound of a clock. So what it means is, again I will draw the signal here. So this is a pulse train, trapezoidal pulse train and it's a periodic signal. So actually, that's what a clock signal looks like for all digital circuits. That's why we are studying this trapezoidal instead of a square waveform or a square pulse train, because that actual signal looks something like trapezoidal instead of a square pulse. So here this part, so this is our rise time, tau r, and this is the fall time, f, and this is the time period t. So means time period means it repeats after every time period t, and so this is, if this is a, so this will be a by 2, and this will be tau. So tau is pulse width. And for all the analysis that we have done in the lectures, professor has discussed for a trapezoidal pulse whose rise time is equals to fall time. So that has been throughout all the lectures that we have seen. Now, what duty cycle is? Duty cycle is the ratio of tau by t. So what are the effects that we have studied is, if you see in the lecture 14th or 13th, I think lecture 13, we have seen that for a trapezoidal pulse train, some duty cycle was there. Let's say the first part it was given as 50%, and then one example was solved. Like when we saw that or something like that. Means this is the DC level, which is for a trapezoidal pulse. We know that is given by a tau by t. So a tau 2 times a tau by t, and the first breakpoint frequency, and this is the second breakpoint frequency. So first breakpoint frequency is 1 by pi tau, and the second one is 1 by pi tau r. So if we notice this, because the duty cycle depends on tau and tau by t, so if we change the duty cycle, there will be a change in this first breakpoint frequency and the DC level. But there won't be any change in the second breakpoint frequency. So that's a conclusion of what has been studied. So we can clearly see that the duty cycle does not change. The duty cycle change, if we make it to 50 to let's say 30%, so this change will not affect the high frequency component of the clock, because this remains the same, right? So any frequency after this will not be affected. Now just a second. So those who have joined just now, we are just discussing what has been done, like what have been discussed during the last week's lecture. So we were discussing the effect of duty cycle on spectral bounds of a clock. So in summary, I can say the duty cycle change does not affect the high frequency components of the clock. It only affects, if we change the duty cycle, the DC level will be changed, and also that first breakpoint frequency will change. But after that, the second breakpoint frequency, which is given by 1 by tau r, will remains the same, because it depends on the rise time and fall time. Because here in this pulse we have considered rise time and fall time both are same. So, but it does not affected by the duty cycle change. And then we also studied the effect of rise time and fall time on a spectral bound of a clock. So if we change the rise time and fall time, we have seen that it will affect the higher frequency components. So if you have a higher rise time, we will have higher frequency spectral content in our signal, and that's what we want. So ideally, we want to have a higher rise time, means this, so that higher frequency components will be less, and these higher frequency components are unwanted. We don't want them because those are the ones which cause interference or EMI EMC issues. And then we have discussed the effect of ringing on the spectral bound of a clock. So what ringing is, so let's we will take what now we are discussing what ringing is in a pulse train. So let's say we have a square pulse xt. This is the time axis. So it's a clock signal to some kind of a digital device. So ideally it should be like this. This is one ideal scenario, but actually it is something like this. If you see, there will be a ringing, means it's not a perfect square pulse. There will be some ringing, means like immediately, let's say it's from 0 to 5 volt. So it won't become 0 from 0 to immediately, it won't go to 5 volt. It will take some time to reach and stabilize at 5 volts. So that's what ringing is. And now we want to see what is the effect of this ringing on spectral bounds of a clock. So that we have seen. So now next, what was discussed was the spectral bounds of a linear system output. So that also we will discuss. Like there, I have put some problems based on that, and during that time we will discuss this. So now let's start with question number 1. So before we start, just let me know if you have any doubt. We can discuss. Or if it is not there, then we will move on to the problems. And I request you to have a pen and paper with you and start. You can also solve along with me the problems, because I will be going slow, so you will have enough time to solve. And if you face any doubt, now itself you can ask. So for question number 1, for a trapezoidal clock, the spectral magnitude is a product of. So it's asking for a trapezoidal clock, the spectral magnitude is a product of. And 4 options are given: a sinc function and a cosine function, 2 sinc functions, a sinc function and an exponential function, a square wave and a triangular wave. So I hope the question is clear. If you have any doubt in this, please let me know. This is the problem, now we'll solve it. So if I write down the expansion coefficient for a trapezoidal clock signal, it is something like this. We have already seen this. It is a tau by t into sine 1 by 2 n omega naught tau, 1 by 2 n omega naught tau divided by 1 by 2 n omega naught tau multiplied with sine sorry about that, I think some issue is there. So I will write down it here. I will write it again. So, just a second. So expansion coefficient for a trapezoidal clock, we can write this as E tau by t into sine 1 by 2 n omega naught tau divided by 1 by 2 n omega naught tau into sine 1 by 2 n omega naught tau r. So here tau r is the rise time and tau is the pulse width. 1 by 2 n omega naught tau r into e to the power minus j n omega naught tau plus tau r by 2. So and here we have made one assumption, like in all the trapezoidal clock signals that we are discussing in the lectures and then this questions. Just a second. Yeah, those who have joined just now, just we have started solving the problem. So we are on problem number 1, and question number 1 is, for a trapezoidal clock, the spectral magnitude is a product of. That means we have to write down the spectrum. So this expansion coefficient Cn for a trapezoidal clock signal or trapezoidal pulse is this, and here we have made one assumption that tau r is means rise time is equal to the fall time. So if we write just the magnitude for a two-sided spectrum, that means we are writing the spectrum the magnitude for Cn plus, which is nothing but 2 times of the magnitude of Cn, and it's equal to 2a tau by t sine x by x. We know that sine x by x is sinc, so its magnitude will be sinc n omega naught tau by 2 multiplied with the magnitude of sinc n omega naught tau r by 2. So now if you observe it, this magnitude of spectral magnitude is a product of two sinc functions. So first one and the second one. So now if you go to the options, the correct option here is a trapezoidal clock. For a trapezoidal clock, the spectrum magnitude is product of two sinc functions. I hope this is clear. If you have any doubt in this, please let me know. So if it is clear, then we will move on to question number 2. In question number 2, how does the first asymptote of the spectral magnitude of a trapezoidal clock behaves if in the frequency domain before the first breakpoint? Okay, so what it is asking us is, so first it is asking about how does the first asymptote of a spectral magnitude of a trapezoidal clock behaves in the frequency domain before the breakpoint. So we will first denote it in the spectral domain or the frequency domain. It looks something like this: F for a trapezoidal pulse. So it looks something like this. So the first breakpoint frequency is given as 1 by pi tau, and the second breakpoint frequency is 1 by pi tau r, and this DC level is 2a tau by t. So here it's 0 dB per decade and minus 20 and minus 40. So those who have joined just now, we are solving question number 2, which is how does the first asymptote of the spectral magnitude of a trapezoidal clock behaves in the frequency domain for the breakpoint for the first breakpoint. So here if you see the first breakpoint is here our first breakpoint is, so this is a spectral bounds for a trapezoidal clock or trapezoidal signal. Means if something like this is there. So now in a frequency domain the spectral bounds look like this for a trapezoidal pulse. So the first breakpoint is, or breakpoint frequency is given by 1 by pi tau. So in the question it is asking us how does the first asymptote of a spectral magnitude of the spectral magnitude of a trapezoidal clock behaves in the frequency domain before the first breakpoint. So if we see this just before the first breakpoint, how it is, it's a constant, it's a DC, it remains constant with the slope of 0 dB per decade. So it's asking what is the behavior of the trapezoidal clock before the first breakpoint frequency. So before the first breakpoint, the first asymptote of the spectral magnitude is flat. The first asymptote of the spectral magnitude is flat. So indicating a 0 dB per decade slope. So this is the slope we can see. So if we match it with the options, the correct option is option A. It remains constant with a slope of 0 dB per decade. I hope this is clear. If you have any doubt in this, please let me know. So if this is clear, we will move on to question number 3. Which of the following does not contribute to the spectral bounds of a trapezoidal pulse train? So it is a trapezoidal. So four different options are given, and it's asking out of all these 4, which does not contribute the spectral bounds of a trapezoidal pulse train. Now for a trapezoidal pulse train, and here one assumption is there, we have assumed that the rise time is equals to the fall time. The envelope is given by A 2 A tau by T into sync pi tau F, sorry, into magnitude of sync pi. It should not be 2. It's sync pi tau r. So this is tau r f. So sync we know sync x is sin x by x. So let it be our equation 1. Now in order to generate bounds for this spectrum, we need to take the log of equation 1 in order to generate bounds for this spectrum, we take the log. So we are taking logarithm for equation 1. And when we do this, we get 20 log 10 envelope is given by 20 log 2a tau by t. And since they are this sinc function is and multiplication in logarithm, we can write it as a addition plus 20 log. Now instead of writing in the sinc, I am writing as a sine pi tau f by pi tau f plus 20 log base 10 sinc pi tau r f by pi tau r f. So now if we see that, so this is what an envelope for a trapezoidal pulse looks like. So here it's 0 dB, it's minus 20 dB per decade, and this slope is minus 40 dB per decade, 2 tau by t. So if you look at, so this the first is responsible for this. So we can divide it into 3 plots. This is plot 1, plot 2, and plot 3. The plot 1 is given by this, plot 2 is given by this 20 log 10 sine pi tau f by pi tau f, and the third part is from this. So plot 3 is 20 log 10. So if it can be sum of these 3 plots. So something like that, that's what I'm saying. But in the problem it is asking which one does not contribute. So if we see the options, 20 log 10 a 2 a tau by t, it contributes, we know that. And 20 log 10 t it also contributes. But if you see the option C, since we are talking about the spectral bounds, and if it is given in this t, it's not correct. So option C is the one which is not contributing to the spectral bounds of a trapezoidal pulse train. So here the correct option is option C. If you have any doubt in question number 3, please let me know. If this is clear, we will move on to question number 4. In order to reduce the high frequency spectral content of a trapezoidal pulse train, 4 options are given and we have to find select the correct one. So it depends. So option A is the rise fall time of the pulse should be made large. Option B, the rise or fall time of the pulse should be made small. Option C is the pulse width should be made large and the pulse width should be made small. So for the high frequency content of a trapezoidal train is due to primarily because of the rise and fall time of the pulse, and pulses having smaller and the small rise and fall times will have larger high frequency spectral content compared to the pulses having larger rise and fall times. So for this we can easily see it if we draw the spectral bounds for this. So I'm drawing a spectral bound for trapezoidal pulse train. So it looks something like this. So this 1 by pi tau, 1 by pi tau r. So this tau r is the rise time. And this is 2a tau by t. 0 dB, minus 20 dB, and minus 40 dB. Now if you see this, as we move along on the right side of the x-axis or the frequency axis, we can see the frequency is rising. And if we increase this tau r, means if we increase the rise time, what it will lead to that high frequency content will be that high frequency content will be smaller. So if we increase tau, so higher frequency will reduce. Like what can be the highest frequency? Suppose if this is some number, and if we and this tau r prime is larger than tau r, then what will happen here is so this will be 1 by tau r prime will be shifted to this left hand side. So if you see that from some frequency it will start, because just after 1 by tau r, the second breakpoint frequency, the reduction is minus 40 dB per decade. So immediately, like it will start dropping, and then there will be less number of frequency content in the spectrum if we increase the rise time. So we can write this in words as, I will write it down here. The high frequency content of a trapezoidal pulse train is due primarily to the rise or fall time. Since in this case we assume that both rise time and fall time are same, that is tau r and tau f of the pulse. Pulses having smaller rise fall time fall times will have larger high frequency spectral content. Will have larger high frequency spectral content compared to the pulses having larger rise fall time. Thus, in order to reduce the high frequency spectrum, so if you want to reduce, in order to reduce high frequency spectral content, or if you want to reduce the emissions of a product, means if you want to reduce this high frequency content, or we can just simply say that if you want to reduce the emission of a product, we have to increase the rise or fall time of the clock. of the clock or data pulses. So if we see the options, like the question is asking us, in order to reduce the high frequency spectral content of a trapezoidal pulse train, what we have to do, we have to increase the rise or fall time. So the rise and fall time of the pulses should be made large. So the correct option is option A. I hope question 4 is clear. If you have any doubt in this, please let me know. So that was the main reason, like why we were studying this spectral content and why we were drawing these kind of spectral bounds or these kind of envelopes for a trapezoidal signal, because all the data signals or the clock pulses, let's say if you have a PCB, there are some traces going through it. So any signal, any data signal or pulse signal will not be a perfect square or a rectangular pulse train. They will be something like this, like a trapezoidal pulse train. And our aim is to reduce the emission so that let's say some IC is there and nearby there will be another IC. They should, since they are integrated circuits, lot of different ICs will be there. And because of this IC1, it should not affect the operation of IC2. If there are some emissions, they can affect it. So we want to reduce them as far as possible. So that's why we are studying these spectral bounds for a trapezoidal pulse train. And if you want to reduce it, one thing that we can do is we can increase the rise and fall. We can increase the rise fall time of the pulse. So this is tau f and this is tau r. So in order to, if you want to reduce it, we can increase this. So here the correct option is option A. Now we will move on to question number 5. If the duty cycle of a trapezoidal clock is reduced from 50% to 10%, which of the following changes in the spectral plot is most significant? So now this question is asking what will happen if we reduce the duty cycle from, let's say, from 50% to 10%. What will happen to the spectral plot of that trapezoidal clock? So first we will start by, let's draw a pulse train, a periodic trapezoidal. So this is our trapezoidal pulse train. So like because since it is asking about duty cycle, what will be the change if we increase or decrease the duty cycle? So let's first understand what duty cycle is. So let's say this is our pulse train with period T. So both of these are same, just sorry for the drawing, but actually both of these pulses are same. And since it is periodic, it repeats after period capital T. So this is tau R and this is tau F, the fall time and the rise time. Let's say here it is A and this is A by 2. So at the width of this pulse at A by 2 is our pulse width tau. So tau R is rise time, tau F is fall time, and tau is pulse width, and t is the period of this periodic pulse string. Now, if we define duty cycle, mathematically duty cycle is the ratio of this pulse width by time period. Suppose if it is 50%, means this ratio is 1 by 2. But if you reduce it 10%, so if it is 50%, it is looking, let's say it is looking something like this. And if you reduce it to 10%, what will happen is it will look something like this. So some changes will be there in the signal, but the time period will remain the same. If we are changing this to 50 to 10%, that means we are changing this pulse width. We are not changing the time or frequency of the signal. It remains the same. Only change will come is this pulse width will, if you are reducing it, it will reduce, and if you are increasing, it will increase. So reducing the duty cycle decreases the pulse width tau, which lowers the DC level, So you won't see the DC level here because it's in the time domain, x of t and t. But if I draw the spectral content of this in the frequency domain, so the DC level is given by 2a tau by t. 2a tau by t. So this DC level depends on, this pulse width tau. So if you reduce the duty cycle, it decreases the pulse width, which lowers the DC level and increases the first breakpoint frequency. Increases the first breakpoint frequency. So first breakpoint frequency is given by as break 1 is 1 by pi tau. And the second breakpoint frequency, attenuation remains governed by the rise time and they are unaffected. Means the second breakpoint frequency will remains unchanged. If we increase or decrease the pulse width, it has no effect because it depends on 1 by pi tau. So in the problem they are asking, if we lower the duty cycle for a trapezoidal clock from 50 to 10%, which of the following changes in a spectral plot is most significant? So option A is a reduction in the DC level and an increase in the first breakpoint frequency. So which is correct, right? Because if you see option B is saying that reduction in the DC level and decrease in the second, so which is not correct. There is no effect on the second breakpoint frequency if you reduce the duty cycle. A reduction in the second breakpoint frequency, which is also not true. Option D, an increase in first breakpoint frequency and increase in the slope beyond, no, which is also not wrong, which is also wrong. So if you want, I can give you one example that professor has solved in the class also. So for example, we can take this. So I'm just giving one example that how changing this duty cycle affects the breakpoint frequencies. So for example, let's take one trapezoidal pulse train whose amplitude is 1 volt, and this pulse train is a 1 megahertz trapezoidal clock Okay, so we are taking a clock signal, 1 megahertz trapezoidal clock, which has equal rise time with equal rise and fall time. Rise and fall time. So the rise time is given as 20 nanoseconds, and the duty cycle is also given as 50%. Now what is asked in the question is find spectral bounds between 1 megahertz and 100 megahertz. Bound between 1 megahertz and 100 megahertz. So we know that the first breakpoint frequency is given by 1 by pi tau and the second one is given by 1 by pi tau r. And the DC level is given by 2a tau by t. And the duty cycle is also given, which is tau by t, and which is 50%. So we can write this as 0.5. So in the problem, we know the time period t is, since it is 1 megahertz signals, it will be 1 into 10 to the power 6, 1 by 1 into 10 to the power 6 seconds, or we can simply write it as 1 microsecond. So now from this we can find the pulse width, which is using the formula for duty cycle. So now we know what is t, capital T, the time period is 1 into 10 to the power minus 6, 0.5, and when you solve this, tau comes out to be 0.5 microseconds. So now using this we can find out what is the first breakpoint frequency, which is given by 1 by pi tau. So when we solve this we will get 0.63 megahertz, and when we solve the second breakpoint frequency, which is given by 1 by pi tau r, and when we solve this we will get 15.915 megahertz, and the DC level is given by, so these things are needed when we draw a spectral bound for that trapezoidal clock signal. So the DC level is given by 2a tau by t, and we get 120 dB microvolts. So, but if we change the duty cycle, if we change the duty cycle from 50% to, let's say, 30%, then what will change? One thing will be this pulse width will change, because now tau will become 0 0.3 microseconds, 0.3 microseconds, and if this is changed, the first breakpoint frequency will be breakpoint frequency will be 1 by pi tau. Since tau is changed, this also will change, and this will become 1.061 megahertz. And second breakpoint frequency remains the same, which because it doesn't depend on tau, it depends on tau r. It still remains 15.915 megahertz, and the DC level will be, it becomes 115.563 dB microvolt. So now what we have observed is, if we reduce the duty cycle, what we will observe is, first thing, a reduction in the DC level, and second, an increase in the first breakpoint frequency. Increase in the first breakpoint frequency. So that's why the correct option for this question number 5 is A. A reduction in the DC level and an increase in the first breakpoint frequency. Now we will move on to question number 6. So in question number 6, for a 1 volt 10 megahertz 10% duty cycle trapezoidal waveform, the level at 100 megahertz for the 25 nanosecond rise fall time is. So in this problem it is asking what will be the level of the spectral content. Let's say if it is coming somewhere at 100 megahertz, what it will be, what will be this level, spectrum level. So now let's solve this. So here the amplitude is given as 1 volt, and time period we can calculate since it is 100 megahertz. So 1 by f, which comes out to be, sorry, the frequency of this cycle of this trapezoidal waveform is 10 megahertz. So 1 by 10 into 10 to the power 6, it gives 0.1 microsecond. And since duty cycle is given as 10%, that is 0.1, and duty cycle is the ratio of tau by t, and from this we can find out tau. So tau will be 0.1 into 0.1 microseconds. So tau is 0.01 microsecond. So now using this we can calculate what will be the first breakpoint frequency, which is 1 by pi tau, and when we solve this we will get 31.83 megahertz. And second breakpoint frequency will be 1 by pi tau r. Since the rise time is given as 25 nanoseconds, so it will be 1 by pi into 25 into 10 to the power minus 9, and when we solve this we will get 12.732 megahertz. And now then the question they are asking what will be the level at, like the DC level. Initially it was, so this is our DC level here, but after the breakpoint frequency it starts dropping. So what will be this? What will be this value at 100 megahertz? That's what we have to find out. And in the lecture 14th, I think professor have derived one formula based on the slope, using the equation of a line and its slope. Since because we know the slope and the point, now we can easily derive this. So we have to find the level at 100 megahertz, which is given by using this formula 20 log. So this is for the DC level, a tau t by a 2 a tau by t. So 2 times a is given as the amplitude of this wave is given as 1 volt. So that's why it's 1. Tau is given as we calculated tau is 0.01 microseconds, and time period of this pulse is 0.1 microseconds, minus 20 log 12.732 megahertz divided by 31.83 megahertz minus 40. For the after second breakpoint frequency it becomes 40, so minus 40 log. So it's asking for 100 megahertz. 100 megahertz divided by 31.83, sorry, 12 point, because that's what the second breakpoint frequency is. .732 megahertz. And when we solve this, we will get 106.02 dB microvolt. Because if you see this here, it is 2a tau by t. This t will get cancelled, but still this voltage term remains here, right? So that's why in this units it is 20, it's in dB microvolt. But here, since it is a ratio of frequency to frequency, it will be in decibels. So it will be, so minus 20 log, for this if we solve, we will get plus 7.9591 decibels minus 35.8041 decibels. And when we add them, we will get, so that's why if you see in the options, there are two options which are pretty similar, only their units are different. So you have to be very careful about the units. So the final answer should be in this, because it is asking about the spectral level, right? And the spectral levels are in dB microvolt here. So the final answer will be definitely in dB microvolts, or at least in volts. It can be micro, milli, or anything. But since in the based on the given values, the answer is coming out in microvolts. But definitely it will be dB volts. So when we solve this, we will get 78.1756 dB microvolt. So if you match with the options, the correct option is option A. I hope question 6 is clear. If you have any doubt in this, please let me know. Because here option A and option B are same. The values are same, but the units are different. So you just have to be careful, because now it is asking for the level at 100 megahertz, and the level means it should be in dB microvolt, or at least in dB volt. So if you have any doubt in this, please let me know. I can explain it again if you want. If it is clear, then we will move on to question number 7. Question number 7, what is the primary reason for ringing in a clock signal? So it's asking about what is the main reason behind the ringing. So the main reason ringing is caused by parasitic inductance and capacitance. inductance and caused by the parasitic inductance and capacitance in the circuitry. So if any unintended inductance or capacitance effect is coming out in the PCB, probably because of the trace lines through which the data signal or the clock signal is traveling. Suppose there are two parallelly running trace lines, means the signal lines in the conductivity path, maybe a metal strip or which allows the signal to flow through the PCB. If they are pretty close together, there can be a parasitic effect, such as the inductance or capacitance, which that's why because of that this ringing is happening. Circuitry leading to oscillations. Oscillations when transitioning because what is happening here is the voltage levels are changing. That's what a data signal or logic signal or clock is. The voltage level is changing when transitioning between logic levels. So what ringing looks like is if I draw a square pulse, so if I draw this x of t, which is a square pulse, it will look something like this. Instead of now immediately going to 0, again here ringing will be there. And when it again next pulse comes, again ringing will be there. So if what is this thing is, this is ringing. So, but ideally it should have been something like this. This x of t should be a square pulse. So this is ideal. And this is what actually happens. So that's what a ringing looks like in a pulse train. I hope this is clear. So now what is the problem is asking what is the primary reason for ringing in a clock signal. So this ringing is caused by the parasitic inductance and capacitance in the circuitry. So the correct option is option B, parasitic inductance and capacitance in the circuit. I hope this is clear. If you have any doubt in question number 7, please let me know. If you don't have any doubts, we will move on to question number 8. The spectral jump in a clock signal at the ringing frequency is given by. So for the derivation, if you see the lecture 14, professor has derived this, the expansion coefficient for a ringing square wave. Expansion coefficient for a ringing square wave is given by. So I'm not giving you the derivation here, I'm just directly writing the result here. So this expansion coefficient Cn is given by V by 2 sinc and omega naught T by 4 into e to the power minus j and omega naught T by 4 multiplied with 1 plus k by V multiplied with p omega r, where omega r is the angular frequency of the ringing divided by alpha square plus 2 alpha p plus p square plus omega r square, where this alpha is the damping coefficient. So alpha is our damping coefficient, omega r is the ringing frequency of the ringing, and p here is, we have just written down this j and omega naught as p just to simplify it. Otherwise p stands for j and omega naught. So the spectral jump in a clock signal at the ringing frequency is given by this quantity here. So I will rewrite it. The spectral jump in a clock signal at the ringing frequency is given by this formula, which is k by v. So k is the amplitude of that ringing, since it is something like this sinusoidal. So if you write down, this is k sine and omega r t, something like this. So this k is the amplitude, which reduces with e to the power minus alpha t. So this damping coefficient is alpha. So with over time it is reducing. So k by v, the spectral jump in the clock signal at the ringing frequency is given by k by v into p omega r divided by alpha square plus 2 alpha p plus p square plus omega r square. So if we match it with the given options, the correct option is option B. So if you have any doubt in this, please let me know. So if the question number 8 is clear, we will move on to question number 9. A 30 MHz square wave is passed through a low pass filter as shown in the figure below. If the square wave has a duty cycle of 50%, the distortion will be minimum if. So they are asking what value of this R should be, so that there will be a minimum distortion. So if you have watched the lecture 15, we know that for minimal distortion, we know that R should be greater than 2L by tau. So I'm directly writing this here, but if you want to see that why it is like that, you can refer to lecture 15. So this R should be great. It should be very large compared to 2 times L by tau, where L is inductance of this inductor, which is given as 1 microhenry here. And given frequency is F naught is 30 megahertz. The square wave which is passing through this low pass filter is 30 megahertz. From this we can calculate the period of this square pulse, which is 1 by 30 megahertz, which comes out to be 0.03 microseconds. So we can calculate the duty cycle. The duty cycle is already given as 0.5, and from this duty cycle we can calculate what this pulse width tau is. Duty cycle is the ratio of tau by t, which is 0.5, T also we know from this tau comes out to be 0.0167 microseconds. So that is R should be greater than 2L by tau. Since we know what L is already, it is given. Inductance of this inductor is 1 microhenry, and we also know the tau now from the duty cycle. So it comes out to be 2 into L is 10 to the power minus 6, and tau is 0.03 microseconds. Sorry, tau is 0.0167 microseconds. And when we solve this, we will get 119.76 ohms. So R is approximately equal to 120 ohms. If R is 120 ohms, here if we made this resistor as 120 ohms, then there will be minimum distortion in this low pass filter. So the correct option here is option B. Oh, sorry, option C. It has to be at least greater than. So R has to be greater than 120 ohms. So any value greater than 120 ohms is it will lead to less distortion in this low pass filter. I hope the problem is clear. If you have any doubt in this, please let me know. If question number 9 is clear, we will move on to question number 10. Which case results in the best reduction of high frequency component in the output of a RC circuit? So this also professor has discussed in lecture 15. So if you see, I can directly write this as RC should be greater than tau by 2. So if for a RC signal, if this value of the resistor and capacitor multiplied R and C should be greater than tau by 2, means the whatever the pulse width is going tau, it should be tau by 2 should be lesser than RC. So or the multiplication of R and C should be greater than tau by 2, because if we draw the spectral bounds for this, let's say V out, the spectral bound looks like something like this. Here is 1 by 2 pi RC and it's 1 by pi tau. So it's minus 20, it's minus 40. So if we see that for the reduction of high frequency our aim is we want to reduce the high frequency components. So if we want to reduce it, we can start we can have R and C which is much greater. So what is happening, what will happen if R and C is greater, right? It can shift more toward the left hand side. Means if RC is greater, is larger, this first breakpoint breakpoint frequency will move towards left hand side. Means the moment high frequency signal comes above, which is above 1 by 2 pi RC, it will start reducing. First it reduces at minus 20 dB per decade, and then the spectrum will reduce at minus 40 dB per decade. So the best way to reduce high frequency component in the output signal in the RC circuit is this RC should be greater than tau by 2. So the correct option here is option A. I hope this is clear. If you have any doubt in this, please let me know. Now we will solve question number 11. Question number 11 is for the ringing waveform shown in figure 3.26a. So that's what I have drawn, right? This is what ringing is. Instead of having a regular pulse train, The ringing signal looks something like this. XT. So for the given ringing waveform, which is shown here in this figure, you have to determine the increase in the spectrum at the ringing frequency caused by the ringing on the square waveform. For this damping coefficient alpha is 5 into 10 to the power 6, and the ringing frequency is given as 30 megahertz, and this V naught here, this V naught is 5 volts. Let's say this is a voltage signal, so it moves between 0 to 5 volts, and the frequency of this pulse is, let's say, I think this data is missing in the question, it should be F naught is 1 megahertz. Means F naught is the frequency of this square pulse, which is 1 megahertz. Now in this problem we have to find the increase in the spectrum at the ringing frequency. In decibels you have to find. I hope the problem is clear. If you have any doubt in the problem, like what it's trying to ask, please let me know. If the question is clear, we will move on to the solution. So in the problem, alpha is given as 0.5 into 10 to the power 6. Ringing frequency is 30 megahertz. Amplitude of this ringing waveform is 0.5, K is 5.5, and V naught is 5 volts. So this is given as delta is K by V P omega R divided by alpha plus P whole square plus omega R square. So this is nothing but I'm writing it from this previous question, where it was asking the spectral jump in a clock signal at the ringing frequency is given by. So it is given by this. So I'm just simply rewriting this in the form, but the problem is asking it is in dB. So increase in spectral magnitude is given by 20 log 10 1 plus delta. So first we will calculate what delta is. So K is 0.5 and P is given as, so P we can calculate. P is nothing but it is Jn omega naught. So omega naught we know, we can find it out because F naught we know is 1 megahertz and ringing frequency Fr is 30 megahertz. So here N will be, since Fr is 30 and F naught is 1, if we take this ratio, N is 30. So P will be J30 into 2 pi into 10 to the power 6, because this omega naught is 2 pi f, and when we solve this we will get J is 1.885 into 10 to the power 8, and omega r is also known because we know Fr is 30 megahertz. So it is, when we solve this, it comes out to be 1.885 into 10 to the power 8. So using this we can calculate delta. So delta K by V naught. K is 0.5, V is 5. Then it is P omega R. So P we just calculated, it is 1.885 J 1.885 into 10 to the power 8 is multiplied with omega R. So omega R is 1.885 into 10 to the power 8 divided by alpha plus P whole square. So alpha is given as 5 into 10 to the power 6. It's already given in the problem. And we have to add it with P, which is J 1.885 into 10 to the power 8 and whole square plus omega R square. Omega R is 1.885 into 10 to the power 8 and square of this. Now when we solve this, delta comes out to be 1.885. So it looks like a lot of numbers are involved and it will be complicated, but now if we can easily simplify it, because here the complex part is also 1.885 into 10 to the power 8 and the real part of this number is also 1.885, and denominator and numerator also easily we can simplify this. So when we solve it, it comes out to be 1.885. And now we have to find this increase in the spectrum in decibel. In dB is 20 log 1 plus delta. And when we solve this, it comes out to be 20 log 10 of 1.885, which is 9.20 decibels. So this is a solution for question number 11. If you have any doubt in this, please let me know. So this question 11 is from textbook only. It's the exercise problem from chapter number 3. So whatever been taught in this lectures, right, in the week 3 lectures, everything you can read chapter 3 of the textbook, and you can try to solve some problems also. There are few exercise problems and few example problems in the textbook in chapter 3. You can try to solve them. And if you face any issues in that, or if you want to ask me some doubt based on those things, you can email me to this my email ID ed22d@smail.iitm.ac.in. Or any doubt based on lecture 3 or lecture 1, so week 1, week 2, week 3, you can just email me and I will reply to that. So that's all for today's session. If you have any doubt or any questions, you can ask me. If there are no doubt, that's all. Yeah.
So the recorded session will be available right now?
Yeah, I will record it and upload it. It's being recorded. I will upload it within half an hour. So it will be available in the link
Okay,
which
I,
is given in.
I joined late, that's why.
Acha, no problem. But the link will be available.
Okay,
I
thank
I
you.
think you know right where to find the link. Link will
Yeah,
be
yeah,
available. Yeah.
I know it.
Okay. Okay.
Last time you guided up.
Okay then. It will be there. You can watch that. Okay. Thank you for joining. That's all for today's session.
Thank you.
Yeah. Thank you.
you.